Hello everyone, this is Ildebrando Perez Reyes. Thank you for having me. My talk is about an idea I have been working on of control for convective motions in a cavity. This idea is based on well-known results of natural and forced convection, so that perhaps the most valuable of this is how to combine these results to come up with a control strategy. Just for refresh, here are the schematics of the natural and forced convection for the case of a Newtonian fluid confined between two horizontal walls and heated from below. As you can see, the forced convection should reduce to the natural convection as the pressure gradients vanishes. So, as the aim is to control the convective motions, the idea is based on the hydrodynamic stability results for natural and forced convection. In this way, some parameters come into play such as the Rayleigh number, the wave number, the Prandtl number, and the frequency of oscillation. Additionally, we would need to consider the thermal nature of the bounding walls. For example, if these are purely thermal conductors or perfect thermal conductors. The hydrodynamics of the fluid layer basically depicts the onset of convection. From the mathematical point of view, the hydrodynamics of these cases is summarized in this slide. The expressions correspond for the situation in which both horizontal bounding walls are purely thermal conductors. What makes so special to these results is that for this case, analytical expressions can be obtained. Then, for natural convection, the Rayleigh number is found as is indicated here. Here, Bi is the Biot number accounting for the thermal properties of the walls. Also, this Rayleigh number has a minimum value with respect to the wave number k, which are also known as the critical Rayleigh and wave numbers. What happened for the case of forced convection in a Newtonian fluid layer heated from below and bounded by purely thermal conducting walls? Again, analytical expressions for the hydrodynamic stability can be found. These are shown in this slide. Notice that in this case, the Reynolds and the Prandtl numbers appear. An asymptotic method was also used to obtain these expressions. What is interesting about these results and those for natural convection is that these for forced convection reduce to those of natural convection as the Reynolds number goes to 0. However, this only occurs under certain conditions. You should notice that as the Reynolds number is increased, the Rayleigh number increases too. In other words, the fluid layer becomes more stable with the Reynolds number. The previous results for forced convection were obtained for a particular situation as presented in this slide. Consider a large cavity in which the top wall moves horizontally, as indicated by the arrow. As the wall moves, the fluid is set in motion too, so that the parallel returning flow is formed at the core of the cavity. At the same time, the bottom wall is heated so that convection is affected by the returning flow, also called principal flow. Around the cavity outside is shown a possible experimental arrangement for the measurement of temperature and further adjustment of the top wall motion in response to these measurements as in a feedback control loop. Here are some thoughts to present how to control the natural convective motions. First, you may find that convective motions are undesirable or not. Or, second, as I show here, you may want that the convective conditions in the fluid layer be those of marginal conditions, for example. Then, one way of keeping always marginal conditions in the layer is by setting the top wall in motion so that the natural convection arrangement is modified in our favor. What is behind this is that you need to monitor the temperature gradient across the fluid layer so that the Rayleigh number can be estimated so that a decision on top wall motion could be made. Here are some notes about the natural and forced convection for a better understanding on how this possible solution works. These details will also help you to have a picture of the conditions maintained in the elongated cavity. So, for short, what is the answer to our question on how to control the convective motions for these conditions? By simply introducing a principal flow, which for our case would be by setting the wall in motion. Going back to the feedback control loop, there are some details that are worth to mention on how this could work. Although this is not an experimental work, it is key to present a possible control loop so that the physics of our theoretical findings may match that of a possible experimental implementation. First, the temperature difference is measured so that the Rayleigh number at any time could be known. Also, it is intended that the convective condition at the fluid layer were that of marginal convection. Then, the measured Rayleigh number should be continuously compared with the critical Rayleigh number. A controller takes this information and makes a decision. If these two Rayleigh numbers are not the same, then the top wall should be set in motion, so that the fluid motion may stabilize the fluid layer, as we previously know from the role played by the Reynolds number. Now, a little deeper into the fluid layer hydrodynamics. As the fluid moves, a velocity profile develops as depicted in the sketch above. This is a laminar flow that can be easily calculated. U0 is the velocity profile for our returning principal flow. Also, since the idea is to use the top wall motion to control the marginal convection conditions, U0 can be used to form an expression for a proportional controller. This controller, as we mentioned it before, shall make a decision on setting the top wall in motion based on this expression for CO, which is the controller output signal. So far, the idea to control the convective motions have been presented. Here, the governing equations are also shown. Next, once the eigenvalue problem for the Rayleigh number is solved, the convective motions should be modulated by the controller signal CO. These equations are also familiar to the linear stability analysis of a fluid layer, so that further explanations are omitted. Those governing equations are solved subject to these boundary conditions. Both walls are solid and the Biot number is kept small to account for poorly thermal conduction properties of the walls. Here is a summary of the procedure followed. If there are any questions, I'll be happy to give further details. So, what is the effect of the controller on the hydrodynamic stability of the fluid layer? The green arrows show the controller signal CO presence on the Rayleigh number and frequency of oscillation expressions. Also, notice that CO is multiplying the Reynolds number terms, which was expected since CO would be equal to 0 if the fluid layer is at its marginal conditions and therefore no fluid motion due to the top wall should exist. Here is a schematic representation of the effects of the controller on the fluid layer. For any value of the Rayleigh number above the marginal red curve, the controller should send a signal to start the motion of the top wall, so that after a while the fluid layer conditions meet those of marginal stability. One side effect of this strategy is that the controller will always drive the fluid layer conditions to meet those of criticality. In particular, As this is the first approximation to the problem, I should recognize that perhaps better results can be achieved if full proportional integral derivative control signal is used, not considered here. This approximation is also based on continuously modifications to the basic state of the velocity, which could also seem odd, but I think that this is physically feasible. Also, this approximation to the control of convection in a fluid layer is another option to the strategy based on modifying the perturbed temperature boundary condition as done by other researchers. Finally, as a side comment, more realistic results could be obtained from a cascade control approximation by combining top wall and temperature at the bottom control signals. Thank you for listening. I shall be happy to answer any question you could have on this preliminary study, and you can also reach me at my email address in this slide as well.